Welcome back. Today we're looking at two features that together form the backbone of Rust's type system: generics and traits. These are what let you write code once and use it many times across many types while still getting full type checking and zero runtime overhead. Generics let you write one piece of code that works with many types, a single function that can find the largest value in any list of comparable items, a single struct that can hold any value, a single vector type, Vec T, that adapts to whatever element type you ask for. Traits let you describe shared behavior across otherwise unrelated types, anything that can be printed, anything that can be compared, anything that can be iterated. A trait is how Rust says, here's a capability a type can have, separate from any particular type that has it. Together, generics and traits give you something remarkable: code that is abstract and reusable, but still fully type-checked and with zero runtime cost. That last bit is the Rust distinctive. Other languages achieve abstraction by giving up performance, by using boxing, dynamic dispatch, or reflection that costs real cycles. Rust refuses the trade. Its abstractions compile down to code as fast as if you'd handwritten it for every specific type. A generic function takes a type parameter written in angle brackets after the function name. The convention is to use single capital letters like T, U, V for generic types, though you can use longer names when clarity demands it. Inside the function, you use that parameter anywhere you'd use a concrete type, as a parameter type, as a return type, inside a more complex type. When the function is called with a specific type, the compiler substitutes that type in and generates a specialized version of the function just for it. This process is called monomorphization. It's how Rust delivers zero-cost abstraction. Generics look flexible at the source level. One function, many uses, but they compile down to code as fast as if you'd written that function by hand for each type. There's no reflection, no type tags, no runtime lookup. The example on screen shows a function called largest. It takes a generic T with a trait bound of partial ord, meaning T must be a type you can order with greater than. It walks through a slice and returns a reference to the biggest element. We call it once with a vector of numbers and once with a vector of characters. The compiler produces two specialized copies, each one tailored to its specific type. Both run at full speed. Structs can be generic too. A point that works for both integers and floats, a pair that holds two of anything, a container that holds any T. The type parameter lives at the top of the struct definition, right after the struct name, and the fields can reference it anywhere they'd mention a regular type. Methods on a generic struct live in an impl block that also declares the type parameter. You write impl angle T, point angle T, and then inside, you can use T freely. In the example, we define point of T with X and Y, both of type T, and a new constructor that builds one. You can then create a point of integers, or a point of floats, or a point of your own custom types, as long as the operations you want to perform on T make sense. Generic structs are everywhere in Rust's standard library: Vec of T, option of T, result of T, E, box of T, hash map of K, V, and many more. All of them are generics. All of them compile into efficient specialized code, and all of them feel first class because in Rust they really are. A trait is a named collection of methods. You define it with the trait keyword, list the method signatures a type must provide to implement the trait, and then any type can opt into the trait by implementing those methods. This is how Rust models shared behavior. Not by inheritance, Rust doesn't have inheritance, but by each type explicitly opting in to a capability. A trait is, roughly, what an interface is in Java, or a protocol in Swift. But because of how Rust compiles them, traits cost nothing at runtime when used through generics. The example defines a summary trait with a single method, summarize, returning a string. Any type can provide its own summarize method by writing impl summary for that type. We define article with a title and body and implement summary for article by building a formatted string from its fields. The relationship between the trait and the type is completely explicit. You can see it in the code. There's no class hierarchy to trace through, no inheritance chain to climb, no virtual method table to guess at. If you want to know what methods a type has, you look at its impl blocks, direct inherent methods in any traits it implements. Everything is visible, nothing is hidden. Inside a trait, you can provide default method bodies. Types that implement the trait get those methods for free and can override any of them if they want custom behavior. This is how the standard library manages to have so many convenient methods without asking every type to implement them manually. Implement one small primitive and a whole family of higher-level methods comes along with it. The example defines a greet trait. It requires one method, name, which must be provided by every implementer. But it also supplies a default hello method built on top of name. Any type that implements greet automatically has a hello method that calls name and formats a greeting. The user struct implements greet by providing only the name method. Hello comes along for free. This pattern is pervasive in Rust's standard library. Iterator, for instance, has one required method, next, and dozens of default methods built on top of it: map, filter, take, sum, collect, and so on. Implement next, and all of those come for free. You can still override any of them if a type has a specialized implementation that's faster, but you don't have to. When a generic function needs to do something specific with its type parameter, compare it, print it, add it, hash it, you use a trait bound. The bound says, this type parameter T must implement this particular trait. Now the compiler knows what T is capable of, and the function can call the trait's methods on values of type T with confidence. In the simplest case, you put the bound right after the type parameter. T:display means T must implement the display trait. You can combine multiple bounds with a plus sign. T:display plus clone means T must implement both. For more complex bounds, especially when multiple type parameters each have their own constraints, use a where clause. It goes after the signature and keeps the parameter list readable. In the example, we have a process function with two generic types, T and U, and a where clause below that specifies T must implement display and clone, while U must implement ord. The same thing could be written inline, but the where clause is easier to read once you have more than one or two bounds. Trait bounds are the glue between generics and traits. They're what lets you write code that's both general and meaningful, because the compiler always knows exactly what operations are allowed on each type. Generics have one limitation. They're monomorphized at compile time, which means every call site must know its specific type. But sometimes you need a collection of values that all share a trait without knowing their specific types in advance. A list of shapes that can all be drawn, a pipeline of handlers that can all process a request, a set of plugins that can all do some common operation. For that, use a trait object. The syntax is the keyword din followed by the trait name, typically wrapped in a box or a reference. A vec of box din shape holds shapes of possibly different concrete types, all accessed through the shape trait. When you call a method on a trait object, Rust goes through a small virtual method table at runtime, what's called dynamic dispatch. This is the one place Rust does trade a little performance for flexibility. Each call costs one extra indirection. In the example, we define a shape trait with an area method. We implement it for both circle and square. We then build a vec of box din shape containing a mix of circles and squares and compute the total area with iter, map, and sum. Most of the time, generics are preferable. They're faster. But when you genuinely need runtime polymorphism, trait objects are there. Generics and traits. Together, they let you write Rust that is both general and fast. This is the combination that underpins almost every serious Rust library in existence. Vec, iterator, error handling, async runtimes, Serde. They all rest on this foundation. Internalize these two features, and everything else in the Rust ecosystem becomes easier to read. Next up, lifetimes, the last piece of Rust's ownership story, and the feature that most often trips new Rust programmers up. See you there.